Welcome to Lab 3 on circuits. The purpose of this lab was to explore the behavior of circuits by building circuits using light bulbs, resistors, voltmeters, and ammeters. We used Kirchhoff's rules by including the node and loop rule to predict the behavior of the circuits we created. From the completion of this lab, we were able to effectively learn how to use Kirchhoff's rules and learn how circuits behave using a hands-on learning experience. We use three main fundamental principles in this lab. First, the node rule describes the behavior of the circuit, where this current flowing into a node must equal the current flowing out of the node. This is because charge, like other quantities in physics, is conserved. The loop rule describes that the sum of all potential differences around a circuit loop will be equal to zero. This can be explained by the concept of path independence and the conservation of energy. The Ohm's law describes the relationship between voltage, current, and resistance. Current is directly proportional to voltage and indirectly proportional to resistance. First, we constructed the circuit as shown here, and we were told to predict the current that would be measured by the two ammeters. The current should be the same in each ammeter. This can be explained by the node rule because the current that enters the first ammeter should equal the current that exits the second ammeter. The total resistance was 147, and the total voltage from the batteries is 3. Using the Ohm's law, we can calculate I, which is the current, and we could calculate it to be 0.02 amps. As we expected, the current in both ammeters was around the same current. Ammeter 1 had 21.1 milliamps, and ammeter 2 had 18.6 milliamps. What would happen if the connection to one of the ammeters was switched? If the connection to one of the ammeters was switched, the magnitude would stay the same, however, the sign would change. We changed the connection for the first ammeter and got a reading of negative 21.1 milliamps. What would happen if we switched the ammeter with the voltmeter? The voltmeter would read 3 volts because there is no voltage drop between the EMF, which is two 1.5 volt batteries, and the voltmeter. The ammeter would read close to 0 volts because the voltmeter has high resistance. The current would no longer reach the second ammeter because it is quote-unquote stopped by the voltmeter. Next, we measured the potential differences across the circuit elements A, B, C, D, E, F, G, and H. As expected, point A showed 3 volts as the EMF source is two 1.5 volt batteries put together. The ammeter measurements are also noted. As expected, the current is around the same magnitude at each location, around 20 milliamps. The sum should theoretically be 0 because we made a full loop around the circuit and energy is conserved, as per Kirchhoff's loop rule. Here's a voltage difference graph that we plotted using the values that we got from measuring the voltage differences across the circuit. As expected, there is a voltage drop at the 47 ohm resistor and an even larger voltage drop at the 100 ohm resistor. As expected, it should go to 0. However, after adding up all the differences, the sum we got was negative 0.6 volts. This could be due to a human error in the lab. What is the resistance of each circuit element? We first rearranged Ohm's law to solve for R, which is equal to voltage over current. We calculated the 47 resistor to be 51.5 ohms, the 100 resistor to be 110 ohms, the wire to be 0 ohms, and ammeter to be 0 ohms. Again, these discrepancies could be described by human error in the lab. Then we connected the voltmeter across the 100 ohm resistor again and noted the ammeter reading. The ammeter reading when we made this change to the circuit was 19.5 milliamps. As expected, the reading was close to the expected 20 milliamps. This is because the voltmeter has a high resistance and has very little current running through it, which leads to the ammeter staying around the same reading. At the top of the slide are the RC circuits that we built. First, we were asked to observe how the light bulbs were changing as the capacitor was charging. While the capacitor was charging, both the 10 and 20 ohm resistant light bulbs dimmed over time. This is because the positive charges on the positive plate start to resist the flow of electrons because the repulsive force becomes stronger. Then, we connected the capacitor directly to the light bulb. Here, we experience the same things. The light slowly starts to dim. This is because there is no EMF that is keeping the voltage difference across the circuit. The 10 ohm bulb lasted for 31 seconds, while the 20 ohm bulb lasted for a minute and 36 seconds while the capacitor was fully charged. What if we charge the capacitor without a resistor in the circuit? Theoretically, a capacitor would charge instantaneously if there was no resistor in the circuit or resistance in the wires that carry the electrons in the circuit. However, real EMF sources and wires have a non-zero resistance, which means that you will never get an instantaneous spike in current to the capacitor. Our resistor took around 50 seconds to get to full charge. There could have been errors in our measurement technique when using the voltmeters. We were also told by the GTA that some of the voltmeters were broken and fixed on the spot by the physics team. There could have also been some interference with the surroundings. This could have caused inflated or deflated readings on the voltmeter. In conclusion, this lab gave us a great opportunity to apply our skills using Kirchhoff's loop rule and node rule to describe the behavior of circuits.